Hello, math teamers. I'm here to just give you a little explanation on how to do mass points specifically with concurrent cevians. So first off, it's probably best for us to know our vocabulary. So a cevian simply is a segment that goes from a vertex to an opposite side of a triangle. So there's our cevian. But when we have concurrent cevians, that means that we have three of these lines and they all meet at a single point in the triangle. So those are concurrent cevians. All right, now we need to understand what a mass point is. And so we've got the old example, and I know you guys are from a new generation without teeter-totters, but back when I was a kid, if you were on a teeter-totter with someone at a different size than you had to scoot up or down so you balance. So here we've got our big kid, and he has a mass of, or a weight in this case, a weight of 100 pounds here. And we've got the little kid here with 50 pounds. And it turns out the relationship for them to be balanced is you have to take mass 1 times distance 1, and that has to equal, oops, I meant 1, fix that up. So mass 1 times distance 1 has to equal mass 2 times distance 2. And the distance is the distance from our pivot point. So this is going to be our distance 1, and this is going to be our distance 2. And so we're going to be putting in our this right around here. Now in order for this to work out, so if we were to put in our numbers, we've got 100 pounds here, and I know that's not a mass, but we're not going to worry about that right now. And we've got 50 pounds right here, and in order for these to be equal to each other, since this is twice as big, we need the distance here twice as big. So let's just say that our teeter-totter is 15 feet long. We could have a distance here of 10 feet, and over here we could have a distance of 5 feet, and that would work out. So there's 5 and there's 10, and we've got 500 equal to 500. Or as it turns out, the distance had to be, so D1 to D2 had to be in a ratio of 1 to 2 in order for these two kids to balance. All right, so now we're going to use that idea with triangles. So here's the type of problem we're going to see with mass points. So in this triangle, we're told that BD equals DC, so I'm going to just mark that they're equal there. And we're told that AE equals 3AC. So that means I'm just going to say that, okay, EC, if I call it X, this one is 3 times as big. So there's my ratio. And now what I'm going to be doing is assigning what's called a mass point to each vertex. So let's say, for instance, if vertex A has a mass point of 1, and say this is like our little fulcrum on our teeter-totter, right? So here I've got 3 times 1. For it to balance, over here I need 1 times 3. And in the examples I've seen, they don't usually put x's. So I'm going to get rid of the x's, but I want you to understand this doesn't mean it's a distance of 1. It's a ratio of 1 to 3. So 1 times 3, 1 times 3. Now if we go back to our teeter-totter example, our total mass on this thing was 150 pounds. We just add the 2 mass points. We're going to do the same thing here. So at E, we're going to have a value of the sum of 3 and 1, which is 4. So we're going to put a 4 right here by our E. Now down here, these are equal, so they were at a 1 to 1 ratio. So if I have 3 here, I'm going to have 3 over there. And then we can see up here I've got a 1 and a 3, and in order for this last segment to balance, I put a 1 here and a 3 here. So 3 times 1 is 3, 3 times 1 is 3, and the total mass at F is the sum of A and B, or 4. And then you'll see a neat thing. Oh, we didn't get our total at D. Our total at D is the 3 at B and the 3 at C, which is 6. And then you'll see no matter which way you add, 4 plus 3 is 7 there for G. 4 plus 3 is 7 there. Or I can take the 6 and the 1 up here and is 7. And I filled out all of my ratios and my mass points. So now if I want to figure out AF to FB, so AF has a distance of 3, FB has a distance of 1, then that ratio is going to be 3 to 1. And if I want to find AG to GD, AG, oh, we didn't figure that out yet. So I've got 1 up here and 6 here. So if I make this a 6 and this a 1, 1 times 6 is 6, 6 times 1 is 6. Okay, we're good. So AG is 6 to GD, which is 1. So it's 6 to 1. And we've got our first problem down. Now, we can use that actually. Oops, that's not the one I wanted. It's gone. Okay. Well, we're going to use this just to explore what we know about medians. So this is a relationship we already know, but we're going to show that it's true using this idea. So I'm going to go through and put in my medians. Remember, a median always goes to the midpoint. That means this is in a 1-to-1 ratio, and this is going to go to the midpoint, making this in a 1-to-1 ratio. And then down here, this goes also to a midpoint. So all of these are in a 1-to-1 ratio, which means that my mass point here at A is going to be a 1, and at B it'll be a 1, because my multiple, 1 times 1, 1 times 1. And you can see how all three sides are going to have mass points of 1. When I find the sums, then I get a 2 here, because A plus B, total mass is 2. B plus C gives me a 2 here, and A to C gives me a 2 here. Let's just call this center point X. And now, let's see, I need some other letters. So let's go with D, E, and F. D, E, and F. And now we can see that ratio of D. If I split this up, I have a mass point of 1 here and a mass point of 2 here, which means this is going to be on the ratio of 1 to 2. And same thing here. Our mass point of 2 on E and our mass point of 1 on C, this is going to be in a 2-to-1 ratio. And the last one, the same thing. I've got a mass point of 1 here and 2 here. It's in a 1-to-2 ratio. And so you can see how our concurrent medians um, divide each other into 1-to-2 ratio. So all right, so let's do one more problem. So in this one, we've got completely different letters, and we're first told that CE to EV is 4-to-1. So put that in, CE to EV, 4-to-1. AI to IV is 8-to-3. And we're supposed to find these others, but before we find it, we're just going to go through and put in our various mass points. So let's start off with, and you can go either way. So for instance, when I did this the first time, I said, okay, I'm going to put a 1 here and a 4 here to balance outside CV. So these multiplied to 4 and these multiplied to 4. And then I got here, 3 times 4 is 12, and I said, well, 8 times 1.5 is 12, but I thought, you know, I really don't want a decimal. And if I double everything, what would happen then? So I went back to the drawing board and said, okay, you know, this would be a lot nicer number if I had 3 here. So 8 times 3 is 24. So 3 times 8 is 24. 8 times 1 is 8, so this is going to be 4 times 2 is 8. All right, so that works out nicely. And then I get my total mass right here is 5, and my total mass right here is 11. And then with the 2 and the 3, I simply do 2 and 3. So I get 6 and 6, and my total mass here is 5. And then my check. So I go 2 at C, 11 here, that adds up to 13. Good. From N to V, 5 and 8 add up to 13. That's good. And I just realized I made a mistake here because I was like 3 and 5. Oh no, because I never erased that one. That was from before. So we'll get rid of that total mass. And our total mass here is actually adding the 2 at C with the 8 at V. That's 10, and 10 plus 3 is 13. So S has a mass of 13. And so now let's figure these out. CS to IS. Okay, now I need to split these up. Now I have a 2 and 11, and so if I simply put a weight of 11 here and 2 here, that'll work out. So CS is 11 to IS, which is 2, so 11 to 2. And then if I want to do NV, I need to work these out. So I've got a 5 and an 8, so I put an 8 here and a 5 here. And so I've got NV, which is 13, to NS, which is 8.